very much for that. How do I do this? This is very complicated. Is this it? Can you hear me? Okay, so I'll just get started. Okay. Is this one mine? No. What happened to my... Oh, no. Sorry, I put it here. Got confused. Okay, so I'm going to tell you about work that's going on in my group right now to combine high force detection sensitivity with magnetic resonance imaging and magnetic resonance spectroscopy. And in the past year or so, we've made a lot of progress, and I think there's a lot of potential for this technology, and I want to share some of those advances with you today. So this picture here hopefully will make some sense towards the end of my talk, but it's basically a cartoon showing how we can do spin control to get very high spectral resolution in force-detected magnetic resonance. So my talk is going to concentrate a lot more on the spin physics than I will on the nanomechanics and the MRFM. And I'd like to thank Alex for a beautiful talk and for all the advances that they're doing in that group, but also to present some of the ideas of magnetic resonance force microscopy. So I'm not really going to focus so much on that topic today. So as Alex pointed out, that conventional or clinical MRI is probably the most powerful application of magnetic resonance imaging, and it's really sort of tailored to work with the human body. So it has a length scale that it works with that's on the meter scale, but because it's a spectroscopic tool, you can get resolution down to a millimeter or below. And what we sense, of course, in an MRI machine are the protons that are in the human body, and they're plentiful. So you can, even though you have only a millimeter cube, you have a whole lot of protons packed into that cubic millimeter. And so the weak magnetism of the nuclear spins can be detected inductively. And this technology can be, of course, shrunk down. The same inductive technology can be shrunk down to the micron scale just by changing the form factor of your inductive detection. And so you can reach the micron scale people have with this technology, and you can take something that's of order 10 to the 19th protons per millimeter cubed and get 9 orders of magnitude by just shrinking your form factor. But of course, what we want to do is operate in this regime, and we want to take this same technology and apply it to things like virus particles that have a length scale of 100 nanometers down to single proteins that have length scales of a few nanometers to 10 nanometers. And there now you need much higher sensitivity. You have far fewer proton spins, and you need a far greater sensitivity. But you'd still like to be able to take much of this, the technology that's been developed for conventional MRI and apply it to the scale. And so that's what really I'm going to talk about today. So the outline of my talk is I will introduce this spin detection platform that we've developed over the years in my group for doing ultrasensitive force-detected magnetic resonance detection, and combining that with nanoscale magnetic field sources that can generate very intense time-dependent, and I think that's a very important part of this, magnetic fields and field gradients that allow us to do really spectroscopy. And so in the last couple of years, we've developed optimal control. We've applied optimal control from NMR community to develop NMR pulses that give us very high fidelity quantum control of nanoscale nuclear ensembles, and we can do a lot of different things with that. So one of the things we've done is to demonstrate dynamic decoupling pulse sequences on proton spins in highly protonated, strongly dipolar coupled solids to get very long coherence times. We've used that to do one-dimensional MRI imaging with a slice thickness that's below 2 nanometers, with a sensitivity down to about 50 proton spins. And so I'm going to talk about these two results today, but in the second half of my talk, I'm going to introduce a new idea, an old new idea, that goes back to Peter Mansfield, actually, who won the Nobel Prize for MRI. In '73, he proposed an idea that you can do diffraction in ordered crystalline solids in the same way that you can do X-ray scattering, and you can get sub-angstrom information, but in a chemically specific way, using NMR, using the same technology that you do MRI with, but it requires capabilities that didn't exist at the time. And now we believe that we can do these kinds of this kind of imaging. So I'll introduce a platform for doing NMR diffraction and wrap up with some future directions. So I'm not going to spend much time on this, again, because of Alex's beautiful talk, but the basic workhorse of this technology is force-detected magnetic resonance. And the way this works is we detect a force from the spins, so you need a field gradient. That field gradient typically is generated, as we've heard, using a static field gradient source like a nanomagnet. And in the presence of some RF field, that creates a resonant volume, which we call a resonant slice. And that resonant slice can penetrate deep into the material that of interest. And I think this is really a key thing that's somehow underemphasized about MRFM, is the fact that you really can get very high spin sensitivity and resolution, but with depth, right? You can actually probe a three-dimensional volume with this. And that's, I think, a unique capability of MRFM that still sets it apart from other technologies. And so if you, in this kind of geometry, where here's my coordinate system, we detect the longitudinal component of the spin, we require a lateral field gradient. So in the longitudinal field magnetic moment couples to that field gradient to generate a force on the lever, and that you can work that out for a 1 Bohr magneton, 1 electron spin in a field gradient of 10 to the 6 Tesla per meter, or 10 Gauss per nanometer. That will generate 10 attonewtons of force. So with good force detection and at low temperatures, you can detect single electron spins this way, and do really very cool three-dimensional MRI imaging. And I think this is still state of the art as for three-dimensional imaging in NMR, where Christian Martino in Dan's group demonstrated a few years ago, or not a few years ago now, almost 10 years ago, I'm old, that you can get sub 10 nanometer resolution, and it really does push the spatial resolution of NMR down to the length scales where biologists would be interested, right? And so this is the technology that's being developed in Christian's group. And so my approach to this problem is quite a bit different in the way that it's done in these papers. The only similarity really is that we also do force detection, but the way we do force detection, or the way we couple the spins, is very different, and it provides both challenges and opportunities. So let me share some of those with you. So we use, as was mentioned, these silicon nanowire resonators, which have resonance frequencies in the hundreds of kilohertz. And so for reasons I don't really have time to get into, it's difficult to couple through a static field gradient source at these frequencies. Okay, so what we decided to do was to generate those field gradients using a time-dependent source. So we actually use currents, and we pass them through a very narrow constriction. This is silver patterned on magnesium oxide. It's a 100 nanometer thick film. The constriction is only 150 nanometers across, and we can push current densities that reach close to, or exceed sometimes, 10 to the 9th amps per centimeter squared. So with those kinds of field current densities, you can generate lateral field gradients that are 10 to the 6 Tesla per meter, comparable to some of the a good strong nanomagnet. But the nice thing here is that you can turn these off. So when we do spin detection, we have a phase where we actually read out the spins through the mechanical motion. So we turn this kind of gradient on to do the readout. But then when we want to work with the spins, we turn that off. And then we we modulate this current at the Larmor frequency. And there we can generate huge B1s. We can generate B1s that are around 400 Gauss. And these are experimentally determined numbers. And so that allows us to do very good spectroscopy, as I'll show you in a minute. The only downside of using this kind of geometry for generating your B1 is that it comes with a very large gradient, which you can use for B1 encoding and imaging, but if you want to use it for coherent control, it's difficult because you can't apply hard pulses because the nutation angle varies all over the place over your sample. But we've dealt with that challenge as well, so I'll get to that in a minute. So the detection protocol we use is this one that my student John Nickel calls MAGIC, and the way it works is that we modulate the current through the constriction at the resonance frequency of the cantilever, which is a few hundred kilohertz, and we create a waveform such that the phase of that modulation changes sign by 180 degrees from this cycle to that cycle relative to some clock that's running at the cantilever frequency. So if you Fourier transform that waveform, it has no Fourier components at the resonance frequency that you're modulating at, but it will have sidebands given by this modulation period. And so in between those modulation periods, we flip the sign of the spin 180 degrees by doing an adiabatic fast passage. So here we apply a RF modulation that's resonant with the spins, and we flip the spin 180 degrees. So when you flip the spin and the sign of the modulation, you get in this product a force that's exactly on resonance. So we drive the cantilever right on resonance with this. And there's lots more we can say about this, but I'm just going to, if you have any more questions about this protocol, I'm happy to talk about it after the talk. But so what we do for spin detection is we modulate for a period of time using this MAGIC protocol. So you can see here this is many, many cycles of the MAGIC protocol. So we read out the Z component of the spin, and then we turn everything off, and then we do an encoding cycle. So here we're doing NMR, and then we do another MAGIC cycle here. And because we detect statistical polarization, the sign of the spin signal continuously changes with some correlation time tau m. So what we have to do is make these measurements faster than that time tau m. This tau 0, which is the length of the measurement, is short compared to this tau m. And so we make a correlation of the measurement you did before the encoding with the one you did after the encoding, and then you do an ensemble average of many, many of these. And what you can show is that the correlation that you measure is the integral over the spin density of the lateral field gradient squared times the expectation value of the Z component of the spin with a unitary transform on sigma Z. This unitary transform is given by whatever you do in your encoding cycle. Okay. So one application of this kind of imaging or this kind of encoding is to do imaging, and you can do Fourier imaging a la standard MRI techniques where you apply gradient pulses. You can apply both Larmor frequency pulses, just static gradient, B0 gradients, that will encode spins along contours of constant Larmor frequency that are what we call these V contours, or resonant RF pulses, so you can encode spins on these U contours. This is work that we did in 2013, and here we're just imaging some polystyrene. This polystyrene has some very short T2. It's highly dipolarly coupled solid, 14 microseconds. So the kind of resolution we got in this image was about 15 nanometers in the Rabi field encoding direction and 11 nanometers in the Larmor encoding direction. The spin is projected onto this curvilinear UV coordinates, but if you use COMSOL, you can back out what the field distribution is, and you can convert back to the Cartesian coordinates, and then you can compare that to simulated data that's based on the SEM image. This is the catalyst particle that's inside, and we're measuring this little polystyrene shell on the surface of that. And we can do that, right? So we showed that we can image with sort of 10 nanometer spatial resolution, which is good. But if you want to get to significantly higher spatial resolutions, you need longer coherence times or bigger gradients. So we wanted to go for the longer coherence times. So how do we do that? Well, we need to do good unitaries. We need to apply decoupling sequences. We can, as I said, we have this big B1 variation. You can't apply hard pulses because the nutation angle will vary all over the place. You can't give a good unitary on your ensemble. So what we did was we worked with David Corey's group at Institute for Quantum Computing, and they developed this technology quite a lot, which is the use of optimal control pulse sequences. So here what you do is you design a pulse that's segmented in time. So this is the entire pulse length, and you cut it into these little wedges, and along each little wedge you vary the amplitude and phase of the RF that you're applying. And what you use is this GRAPE algorithm, this gradient ascent pulse engineering algorithm, to vary the you start with some random amplitudes, and then you say, look, I have some initial state, and I want to transform to a final state. Let's say that's a pi over 2. And I want to do that for all for spins experiencing B1s that maybe vary by a factor of 2. How do you do that? How does a single pulse give the same unitary for all those different spins? Well, the spins have to take very different trajectories on the block sphere, but you can find pulses that do this. And this gradient ascent algorithm finds that pulse for you. Okay, you just let the computers grow, crunch for a few days, and it will find this pulse. But it's even better than that, because during the length of the pulse, you can have unwanted Hamiltonians that evolve. You can have dipolar Hamiltonians that evolve that give you dephasing. You can have stray external fields that give you dephasing. You can refocus those Hamiltonians as long as you know what they are. And so this was David Corey's contribution. He included average Hamiltonian theory into this unitary. So it's one pulse that does many different things. So let me get to that in a minute. So we wanted a pulse that acted on spins that had a Rabi frequency between 600 kilohertz and 1.2 megahertz. Very large range, right? And moreover, we wanted a pulse that decoupled spins, the dipolar interaction of the spins, because these pulses tend to be rather long. Because you want to cover this big range in B1. You can't have a very short pulse. Even though your B1 is huge, you still need a rather long pulse. If your T2 is 14 microseconds and your pulse is 13 microseconds, you're going to run into trouble. So we wanted to decouple the dipolar interaction. So you write down the first order Magnus expansion. This is the first order term in the Magnus expansion from average Hamiltonian theory, and you enforce that over the length of your pulse, this term is 0. Okay? So the dipolar Hamiltonian has a very interesting structure. Its sign changes depending on how two spins are oriented with respect to each other, right? The sign here is 1, and the sign here is -0.5. So you can find an average, you can find a trajectory such that the average of the dipolar interaction is 0. So this trajectory must also do this. And if you have any stray external fields, like chemical shift offsets, we want to make those 0 as well. So this pulse does that. This is the amplitude of the real part of the pulse, that's in red. This is the two quadratures of the pulse. This is the amplitude. So the bandwidth of the pulse is also huge. It's 10 megahertz. Our center frequency, our Larmor frequency, is 48 megahertz. Okay, the bandwidth of the pulse is comparable to your Larmor frequency. It's a really crazy pulse, but here's what it does. So this is the pulse in time. This is actually what it looks like. And let me start this animation. So we're going to start from state E. We're going to evolve to state F. I'm showing two different Rabi frequencies on the extremes, 0.7 megahertz and 1.2. Okay, let's let this go. This is the actual calculated trajectory. you can see that these spins take very different trajectories on the block sphere. And what these trajectories are doing, they're averaging the dipolar interaction, they're averaging sigma z, and they make sure that when you reach 13 microseconds, boom, they land back together. We should have called that magic. So that pi over 2 pulse that incorporates average Hamiltonian theory is what we write down as this capital omega. Okay, that's my notation for it. Capital omega pi over 2x refers to a pi over 2 about x pulse with OCT. This is back-to-back pulses, okay, applying up to 250 of them. There's no error correction here, right? We're just, any errors that you accumulate on the unitary gets accumulated, right? So we wanted to see how bad how good, what's the worst case for these pulses, right? So the red is actual data on this small spin ensemble. And you can see that it goes these are in increments of 5 pulses. So you start from the identity, then if you apply an odd number of pi halves, your z projection is 0. And then so you go minus, plus, so on, and it decays. And the sort of the 1 over e decay here corresponds to 100 pulses, which is a pulse fidelity of 99%. If you're doing qubits, this is trash. But if you're doing NMR, it's not bad. And in fact, you can calculate the full 8-spin quantum simulation for the styrene molecule for this pulse. You can propagate this pulse with how would it actually behave. And it's these green dots that you see here. So in fact, we can, by further optimizing the pulse, we can in fact get to better and better fidelities. We didn't push it beyond 99% for this experiment. Each pulse is 13 microseconds. 1300 microseconds. Yeah. Question?
I'm confused because 13 microseconds is rather long compared to the force sensor period.
No. So this is many measurements at one particular. So we pick some n here, right? And then we do this on the encoding phase. We apply, let's say, 5. You apply 5 back to back. You do magic before, magic after. You do a bunch of those. You do the average correlation function, and you plot it.
So do I understand correctly that very importantly here, there is no field gradient while...
Yes.
I mean, if the cantilever were moving...
Yes. There's no field gradient.
In the field gradient, this would not work because the pulse is longer than the period.
That's right. That's right. That we can turn off the field gradient. That's really important.
Or we should know exactly how the cantilever is moving and feed that into this number class.
Okay, let me go on. So look, you can't do imaging. You can't do imaging while you have OCT going on. You're doing all this decoupling, but you can't apply any gradient pulses because it'll screw up the OCT. Okay, so you have to have some other composite pulse sequence where you have some free evolution periods where you can do something. So we take a standard pulse sequence from a solid state NMR. It's called the magic echo sequence. The way it works is, so you don't have to have OCT to understand magic echo. So imagine these are just regular pi halves pulses. The way it works is you rescale the dipolar Hamiltonian. So this pulse sequence comes from average Hamiltonian theory, where you have some period tau, so you create some coherence here with your pi halves pulse that lasts a time tau. So during that time tau, T2 process is active, spins dephase rapidly with, in this case, 11 microsecond dephasing time. But what's your spins haven't, that magnetization hasn't gone away. You can refocus that magnetization. And the way you do that is you see, this cartoon is supposed to demonstrate this. The spins dephase during this time tau. With this pi halves y pulse, you take that whole dephased plane of magnetization and you rotate it about the y-axis by 90 degrees. Now you irradiate with a strong RF field in the x direction, like this. So you let it precess around this effective field for a time 2 tau. Now what happens in this period is the dipolar Hamiltonian here has a scaling of 1 because the spins are in this plane. But when you rotate the spins 90 degrees, the scaling here is -1/2. If you evolve the spins with this orientation for twice as long as you do this orientation, the average dipolar evolution here is 0. Okay? So you do this in a symmetric way. You flip it around, and what forms after a time tau is the spin echo as this dipolar evolution is rephased. And so here we stroboscopically map that out in our sample using these omega pulses, and you see you get a very nice spin echo at the end. So these unitaries really are acting on all the spins in the same way, right? It's a good unitary. And now you can take that magic echo sequence and then you can build it into a larger structure that does more. This is just to correct for unitary errors that accumulate in the way you do the pi halves. So you create superpulse. Sorry? How many spins are there? Well, the entire ensemble that we worked with probably had around 1 million spins, nuclear spins. We measured slices that had as few as 100 spins. So yeah. So I'll get to that in a minute. So, but what we're doing here, this is again a what's called a symmetric magic echo sequence that was developed in David's group in 2003. And so you can have symmetric magic echo 4, so where you have 4 magic echoes, or this is symmetric magic echo 16. You have 16 of these magic echoes. And what we did was we applied these sequences back to back. And again, we stroboscopically mapped out the envelope of that spin coherence as a function of, well, this is the total evolution time, and this is just in terms of the number of sequences we applied. You can see that 11 microseconds of T2 star with SME4, we made it 2.9 milliseconds. With an SME16, we got it up to 5.6 milliseconds. So 500 times increase in the coherence time by doing this. Okay, so you can use some of that extra coherence time for imaging. So what we again encoded in the B1 gradient. This time we did that by changing the symmetry of the magic echo sequence. We just offset the amount of time it evolves in this plus x and minus x directions, and this offset allows you to encode a gradient in the B1 in the B1 gradient. This is the SEM of the nanowires that we use. We have a very thin polystyrene coating. These are the contours of B1 that we're encoding. Again, this is as a function of time defined as 8 times this offset time. So in one SME4 sequence, for a given delta t, the total gradient evolution is 8 delta t. So this is in units of 8 delta t. This is the signal that you get up to an encoding time of only 6.7 microseconds. This is up to 20 microseconds. But even we can't really go much beyond 20 microseconds, even though our coherence is milliseconds, because what happens is that the slice gets so damn thin that we don't have enough spins to measure anymore, right? So, but we use this kind of imaging to at least calibrate what our gradients are. So here is so what we made this measurement in 2 different locations. We physically moved the tip back 10 nanometers. We had a calibrated piezo for doing that. So these are 2 different measurements taken 10 nanometers with 10 nanometer spacing. If you do the Fourier transform of this data set, you get the Rabi frequency distribution on the sample. Here's the red, here's the blue. You can see most of the spins in the back don't get a shift because you're really far away, so the Rabi frequencies are low. But the ones near the constriction that feel the largest field gradients, there you see an offset, and that offset is 1.2 megahertz. So 1.2 megahertz, 0.12 megahertz shift in 10 nanometers gives you a gradient of 2.8 Gauss per nanometer, which is exactly what COMSOL told us we had. So that was a validation of what our B1 gradients were. So this is just basically taking these two different data sets and offsetting them by 10 nanometers. You can see that the best fit was 9 plus or minus 2 nanometers. So we really have a good sense of what our gradients are. If you image with finer resolution, 20 microsecond encoding time. So the slice thickness here was 1.8 nanometers here and 2 nanometers there. The amount of spins that we have in that slice is about 100. That is the net spins. Of course, you have more like 10 to the fourth because you're measuring the square root of n. That corresponds, the corresponding force sensitivity for these measurements were 0.2 attonewtons squared. And that corresponded to about 50 proton spins. Okay, so you have a very long coherence times. You have large field gradients. That means you can encode very large phase differences on the atomic scale. So if I take 2 proton spins separated by 3 angstroms, and these are the experimental numbers for our gradients, this is the B0 gradient, this is the B1 gradient, and you ask, if you put it into an SME16 sequence, and with 3 SME16s applied back to back, what happens, how much phase can you encode for 2 spins that are 3 angstroms apart? 33 pi if you're encoding with B0 gradient, and 26 or 20.6 pi if you're encoding with the B1 gradient. That is a phenomenal phase on the atomic scale, and that allows you to do something called Nmr diffraction. And let me just skip to what that is. It's a very basic idea, which is, if I just think about it in one dimension, if I have a periodic set of spins and I have a linear field gradient, this is the phase, and I evolve the spins for some amount of time in that field gradient, some amount of time tau, then the phase of each of these spins is given by this unitary transform around, let's say, the x-axis, and with this angle. And if you match that angle so that every spin gets an integer multiple of 2 pi phase rotation, and you measure the entire ensemble, you have a coherent signal because all the spins line up in phase with what they were originally, right? So you have a, you get a, mathematically it's extremely simple to write down. Your correlation function is just proportional to the sum over the cosine of this angle. So once you match that angle, once you make this 2 pi, right, you have a peak that has an amplitude of n that goes like n and a width that goes like 1 over n. So it's exactly like a diffraction experiment. So this is an actual device that so what you need here is a linear field gradient, and moreover you want it in all 3 spatial directions if you want to encode a lattice. So this is a device that we're actually making. So it's a 2-layer device. You have a bottom layer, which is your constriction. I'm taking a cross section right here. These are all the leads coming to this central area. Here's my constriction, which you can see here. We put down about 5 to 10 nanometers of ALD to cover it, and then we put a top layer on above that ALD, and these 4 gradient wires generate the field gradients for doing the encoding. And so this is kind of a cartoon of what this will look like when it's done, but this is an actual SEM of the device. So this, to give you a sense of length scale, these bars here, this is all made out of aluminum on aluminum oxide. This is 700 nanometers. That's about 150 nanometers again. And so we're getting very close to actually testing this device. But let me just share with you how this generates linear gradients. If you pass currents, let's say in the x direction, in the same direction, so you want to pass currents in the same direction on the 2 sides, that produces, this is an actual COMSOL simulation of the field in the center, a field that varies linearly, let's say the BZ field that varies linearly as a function of y if I'm passing current in the x direction. And for current densities of 2 by 10 to the 8th, which we've demonstrated we can do, you generate about 3 by 10 to the 4th Tesla per meter of a linear field gradient in the center of that device. And of course you can do the same thing in the other direction to generate another linear field gradient. And you have one more component, which is if I modulate the field at the Larmor frequency, the B1 field, which is in the which I can make circularly polarized, right, is has a z dependence that's also linear. That's also, so all these numbers are the same. So it's 3 by 10 to the 4th Tesla per meter if I set up this, if I pass flow currents in this way. Okay, so I can have linear field gradients in all 3 spatial directions, and that gives me an encoding wave number for doing NMR that looks like that, right? So I can apply these field gradients within a magic echo sequence in the following way. I can apply these B0 field gradients, BZ, dBz dx, dBz dy, in the laboratory evolution periods to encode phase, and I can apply the rotary, the B1 field gradient in the rotating frame portion of the magic echo sequence to encode a phase in the z direction. So what we're working on right now is to use a sample of indium phosphide grown as a nanowire to measure the phosphorus spin lattice. So this is work done by Dan Delacou, who's at the National Research Council in Canada, that grows these beautiful wires. This is the structure. He can grow them as a pure Wurtzite structure. The c-axis spacing, the c-axis lattice constant is 6.8 nanometers. This is a TM image. They're spaced by 3.4 angstroms. So you need then for phosphorus, you need a gradient of 1.7 by 10 to the 4th Tesla per meter for coherence times of 10 milliseconds, which we think we can get in this system. So that would allow you to get a phi of 2 pi and allow you to encode this phase. So then this is an actual, well, not an actual, but this is a calculated field profile, or sorry, coherence profile of the phosphorus spins using the COMSOL simulated field. So we think we can generate a region of about 100 by 100 by 30 or 40 nanometer thick area where you have a coherent phase after doing this encoding. Now this is really brutal, right? Because you want to encode phase that's 2 pi, you know, an integer multiple of 2 pi every time you go 3.4 angstroms in this crystal. So it's phenomenally sensitive to how linear your field gradients are and so on. So it's a very challenging experiment. But if this all holds together, we can generate forces from from these phosphorus spins of order 40 atternewtons squared, and that's a very measurable force for us. So we think we can do this. So looking ahead, so we can apply this kind of technology for looking at nanocrystalline materials, we think, possibly protein nanocrystals, and importantly, you can apply this kind of coherent control to do Hamiltonian engineering in 1D spin systems like fluorapatite, which has been used by the NMR community to do Hamiltonian engineering, where you can engineer different kinds of either Ising or Heisenberg type Hamiltonians for simulation. So I'd be happy to talk about these topics, but I'm probably way over time already, so I'll stop here. Thanks for your attention. And one other thing, this is the group in Waterloo. The early work was done by John Nickel, who's now a faculty member at University of Rochester. All the work in my group done on OCT was done by Bill Rose. Angela Chen made the constrictions for us. Holger Haas is a very talented student from David Corey's group, who'll be joining me as a postdoc in April. Michelle is making all the NMR diffraction devices. Ben Yeager is basically a jack of all trades, building the lab with me, and Andrew and Sahand are 2 master students working with me. So thanks for your attention.